Assalamualaikum, we are from Group 27 and we will be presenting an article critique on an article about cumene production through process simulation and sensitivity analysis published by Hilman Ali in 2022. Before discussing the research, it is very important for us to know that cumene is a petrochemical compound that is mainly used as a raw material, and improving its efficiency is significant in the industry. This study aims to optimize cumene production by developing a steady-state process simulation using Aspen HYSYS version 10. The researchers modeled an integrated alkylation and transalkylation process where benzene reacts with propylene to form cumene, and then the unwanted byproducts are converted back into cumene. Using sensitivity analysis, the researchers identified the operating optimum condition. The results showed that a benzene to propylene molar ratio of 7, a temperature of 170 degrees Celsius, and a pressure of 3 megapascal achieve a 99.99% propylene conversion and 0.9446 of cumene selectivity.
First, regarding the clarity of the research question, the study's purpose is generally easy to understand. The authors wanted to develop an Aspen HYSYS simulation that could produce 10 tons per hour of cumene at 99.99% purity. They also examined how the benzene to propylene ratio, feed temperature, and pressure affected conversion and selectivity. However, the article does not state the research question directly. Instead, the reader has to identify it from the objective section. Also, the term optimum conditions could also be clearer because the study mainly uses conversion and selectivity to decide the best conditions, rather than including factors such as energy use or cost. For the appropriateness of methods, Aspen HYSYS was a suitable choice because the research focused on simulating a continuous chemical process. The model included the main reactors, separation columns, heat exchangers, pumps, and recycle streams needed for cumene production. The authors also used fixed bed reactors with zeolite catalysts and included reaction rate equations for the main reaction, side reaction, and transalkylation reactions. These methods were based on previous studies and matched the research objective. Sensitivity analysis was also appropriate because it allowed the authors to study how changes in molar ratio, temperature, and pressure affected reactor performance.
Okay, so moving on to the validity of results and data interpretation. Overall, the findings are highly valid and align well with industrial cumene production. The Aspen HYSYS model achieved full convergence, yielding 99.99% propylene conversion under the optimal conditions as stated in the slide. The sensitivity analysis further proved this validity, where the trends logically reflect reaction kinetics, where extreme 170 degrees C or the 7:1 ratio promotes unwanted side reactions. Furthermore, operating at a threshold pressure at 3 megapascal keeps the reactant strictly in the dense liquid phase, preventing catalyst hotspotting, optimizing mass transfer, as well as resists polymerization. In short, these results accurately reflect true thermodynamics behavior and establish a solid, realistic process baseline.
Although the study provides valuable findings, it has several limitations. First, the results are based entirely on Aspen HYSYS simulation without comparison to pilot scale or industrial data. Therefore, the reported optimum condition may not fully represent the actual plant performance. Second, the sensitivity analysis only considered 3 operating variables, which are the benzene to propylene ratio, the reactor temperature, and also reactor pressure, while other important factors are kept at constants, such as the reactor design and catalyst deactivation. Lastly, the optimization focused fully on conversion and also selectivity. However, as highlighted by Lubin, achieving higher selectivity also increased the capital and operating costs. Therefore, economic evaluation should be included before the proposed operating conditions can be considered practical for industrial application.
Okay, now I will be explaining the significance, relevance, and also the ethical concerns of these findings. So first of all, one of the base influences is its cost efficiency. Cumene production is maximized by converting the unwanted byproduct, p-diisopropyl benzene, back into cumene through the transalkylation process. So as a result, the industry can prevent unnecessary spending on expensive feedstocks, which are benzene and also propylene. And other than that, these findings also important to determine the optimal benzene to propylene ratio. So in this article, benzene to propylene ratio was selected as 7 because it achieved 99.99% of propylene conversion and also 0.9446 of cumene selectivity. So it can prevent propylene self-reaction and also blockage. And with this ratio, excess benzene can absorb heat and stabilize the reactor. And then in terms of industrial relevance, it meets commercial standards, which is this process uses environmentally friendly catalyst, which is zeolite, instead of acidic catalyst. So it can prevent corrosion and also promote sustainable operation. And last but not least, although this article does not explicitly mention the ethical concerns, but we can see that this process is benzene, which is a toxic and carcinogenic substance, and also works under extreme operation conditions. So this highlight the importance of identifying possible hazards, protecting employees, and complying with safety regulations.
Overall, this study provides a valuable scientific contribution by proving that the process simulation and sensitivity analysis are effective approaches. However, although the optimum operating conditions are successfully identified, additional validation is required, such as experimental or industrial data, to improve its applicability. Overall, it is a useful foundation and references for future research, as this article provides a reliable approach for improving the chemical process design and optimization. That's all from our group. Thank you.